All right, let's talk about minimizing a quadratic in multiple dimensions. So here's our objective function. Go ahead and solve this problem, minimizing this with paper and pencil. Basically the same stuff we did in the one-dimensional case, but in multiple dimensions now. Try to use linear algebra if you can, rather than summation notation. So pause the video while you do that. All right, welcome back. So we need to take the derivative of this, or the gradient of this whole thing, and set that equal to 0 and solve. So what's the gradient of x transpose qx? It's 2x transpose q, just like the derivative of ax squared is 2ax. And the gradient of b transpose x is just b transpose. Then we set that equal to the 0 vector. We subtract b transpose from both sides, and then we kind of divide by 2q, but really you can't divide by a matrix. So you multiply both sides by q inverse, and so you get x transpose equals -1/2. The negative comes from subtracting b transpose from both sides. -1/2 b transpose q inverse. And that looks a lot like the funny way we wrote the Newton's method, the vertex formula up here, right? Negative b over 2a, but we can write it as -1/2 b times a inverse. And that's what we're doing here, except we're calling it q instead of a. We're not used to saying here's x transpose, so we can go ahead and transpose this whole thing to get just plain x. And when we do that, you have to switch the order of the product when you transpose it, and b transpose ends up being b. And we're presuming q is symmetric, because if it isn't, we can use a symmetric version of it. And so the transpose of q inverse is just q inverse still. So that's a little bit more familiar doing a matrix times a vector. Maybe we like that. One thing, we like writing this, like from linear algebra class, we like writing a inverse times b. But if you think about how long it actually takes to compute, it takes longer to compute an inverse and then multiply by a vector than it does to just solve a system like matrix times vector equals known vector. It takes about 3 times longer. So while we write this, we would actually solve it, if we're being careful, by solving the system rather than taking an inverse. Also, the Hessian is sometimes sparse. Most of the entries are 0. But then its inverse, even the inverse of a sparse matrix is usually not sparse. So there's special ways of storing sparse matrices and processing them that go faster. So we really don't want to do stuff with the inverse if we don't have to. We'd rather just keep the original matrix around and solve systems. So that's just a little bit of linear algebra advice, and here's some references for that. And then next video, we will take this idea of minimizing a quadratic in multiple dimensions and turn that into a multidimensional search method.